Good afternoon, good morning, sorry, one and all. We'll begin our second class today, that is part 2 of module 4, which is microcontrollers. Yesterday we had a clear discussion about flip-flops and latches and how they are used. So today let's move on to the second part of module 4, which is microcontrollers. Microcontrollers, as we know, are foundation elements for most of our modern equipment today, and it is used in our digital computers and so many logic circuits. And today we are going to discuss and have a very brief introduction and architecture about microcontrollers. And the textbook is the reference textbook given in your syllabus book, that is the 8051 Microcontroller and Embedded Systems using Assembly Language and C by Mohammed Ali Masidi by Pearson Education. So, microcontrollers, in short, we will call them as MCUs, microcontroller units. Okay. The objectives of our study today is to understand what is a microprocessor and microcontroller, to understand what is the difference between both, to know what are the basics of microcontrollers and how its architecture is to be designed, and understand that architecture of a very popular microcontroller family, that is MC8051. So, all these let us see today. So, first let us see what is a microcontroller versus a microprocessor. Microcontrollers are designed for special purpose, whereas a microprocessor is a general purpose device. So, that is the first basic difference we have to understand. Microprocessor is a general purpose device, whereas microcontroller is designed for a very specific purpose or application. And then, so no external components are needed for a microcontroller, because everything what is needed, that is all the peripherals, will be on the single chip. It is a system on chip. So, all peripherals plus the CPU will lie on one single chip in a microcontroller, whereas in a microprocessor, memory and other peripheral components like the UART to send, receive and whatever, any external component, it would be outside the CPU or outside the chip, and it should be interfaced with the chip or added to the chip separately. So, microprocessor board, it will come as a general purpose board where everything is external, memories are external, then all other interfaces, other peripheral interfacing devices are externally connected, whereas in a microcontroller everything is there on a single chip. So, the major differences which are to be identified between a microcontroller and a microprocessor is, first let us see which, based on the parameter, the definition of a microprocessor. So, a microprocessor is a clock driven IC which can perform all ALU related operations. What is an ALU? ALU is arithmetic and logic unit. It is one of the foundation blocks present to compute all arithmetic and logical functions. So, to do all arithmetic and logical functions, we have one combinational logic circuit which is present, which is the ALU, arithmetic and logical unit. And whereas a microcontroller can be called as a self-contained system on chip. What do you understand by self-contained? Self-contained means everything is present on the chip itself. That means nothing needed to be added extra. So, it is a completely self-contained system on chip. The next parameter is usage. So, as I have already mentioned before, it is a microprocessor is used for general purposes. So, any purpose, anything we want to do with a microprocessor, you can design your application and use it. So, it is a general purpose device. It is available as a general purpose programmable board where you can type in your instructions as a program and execute them. Whereas in a microcontroller, it is application specific. So, for one particular application, you are going to use one microcontroller. You will design a complete microcontroller based structure for every single application. It is a new chip or new board. Then coming to the internal architecture, The microprocessor has the arithmetic logic unit or the ALU control unit and all general purpose registers on the chip, whereas the memories, random access memory RAM, read only memory ROM, the input output ports, the timers, counters and communication module for serial and parallel communication and interrupt structure, they all should come externally. So, in a microprocessor, what is there on board? You just have the ALU control unit and the general purpose registers and maybe a small amount of program and data memories. So, only so many things come on board and everything is additional or it should come from the outside. Whereas in a microcontroller, RAM, ROM, IO ports, timers, counters, communication modules, everything is there on the single chip. So, everything comes on the same chip and hence it is a self-contained device. So, in detail we are describing it. The next parameter is what is the emphasis to be put on while designing a microprocessor? While designing a microprocessor, the emphasis is on the flexibility and performance of the device. So, how flexible it is, what different types of programs I can do on it, what other application I can use it for. So, it should be quite a flexible device and it should allow me to do anything what I want because it is a general purpose board. Whereas, microcontrollers are designed for single specific applications. So, the design emphasis then will be on reduction in cost and reduction in size. So, how small I can make the device. Since I am using this device only for this application, I should see that how small the device can be made, like our mobiles for example, how we can reduce the size, how we can reduce the cost, how you can reduce the power consumption, so on. So, the emphasis is on such issues in microcontrollers. The user interface, you have a generic user interface like keyboard, mouse, printer, so on for a microprocessor, whereas in a microcontroller the user interfaces are tailored as per the application. So, based on what application it is, the interface would be different. Say for example, for a TV remote control, you just have to have some buttons and the unit. So, for a remote controlled car, I will have a separate remote control and on that I will have some maybe joystick or keys. So, what I should interface depends on the application in a microcontroller. Performance, the execution speed is much lesser in a microprocessor. It is naturally because everything should be fetched from external devices. So, ROM, RAM, all memories are externally connected. So, by the time all the things are fetched, data, program, everything is fetched, you surely need additional time when it is outside the CPU or outside the main unit. Whereas in a microcontroller, everything lies on the same chip. So, surely everything could be fetched in lesser time. So, speed is higher. In microcontroller, speed is higher. Finally, the applications, just some example applications I am telling. PC, the personal digital assistant or PDA, the cell phone are some of the applications of microprocessor, whereas a digital watch, TV remote control or any remote control for that matter, garage, car remote control and all so many other common day-to-day appliances are fitted with microcontrollers. So, these are the fundamental differences. The example devices for microprocessors are 8085, 8080 and 8080 was one of the oldest, Zilog, manufactured by the company Zilog, 8085 which came next, 86, then we have 186, 286 which goes to Pentium and additional today. So, we have all our processors which we generally use in our laptops, in our PCs are microprocessors, whereas microcontrollers are used in simple appliances which we use in our day-to-day life. The example microcontrollers are Intel 8051, MSP 430, the PIC microcontroller. It's a PIC stands for Peripheral Interface Controller. So these are the major differences between a microprocessor and a microcontroller. So today we are going to study about microcontrollers. Microcontroller can just be defined as a programmable digital processor with all the necessary peripherals. It can also be called as a sequential digital circuit, a very complex sequential digital circuit which is meant to carry out a job according to a program or set of instructions which we are going to give it. So you can write a program. A program is nothing but a sequence of instructions in a language which can be understood by the controller, and the controller will then take that program and execute it. So sometimes, though I call it as a digital processor, sometimes it can also be called as a mixed mode device because of the interfaces where we have analog input and output devices. So for example, a microphone, or you have a speaker, you want to interface some analog input and output devices. So our speech should be transmitted. I will interface a microphone and then on the receiving side a speaker. So then it becomes a mixed mode device rather than a digital processor. This microcontrollers can be defined or considered as self-contained systems with a processor, memory and I/O ports, and in most of the cases everything is present. The only thing which should be added additionally or externally is the program or software to define what is the operation of the system. So you have robots designed today and so many things. All you need to do is just add an additional software or program. You write a set of instructions to make the device listen to you, work according to your requirement. Let's take an example system here of a microcontroller. A remote controlled car we are taking as an example. So this is the car and this is the remote control for the car. So in the remote control, I would have the keys for forward, backward, left and right movements, and these movements or controls, what I need to do, I should control it through 4 different keys, or sometimes maybe just 3 keys, or a joystick. In different gaming applications it is different. So these things are interfaced onto a microcontroller, and from the microcontroller it should go through a RF transmitter, a radio frequency transmitter, through a antenna. You have a very small antenna on this, you can see it here, and it should be transmitted. The instruction what you give, whether you want the car to move left or right or front or back, whatever instruction you give, it will be transmitted through this transmitter to the car. In the car you have a receiving system, you have a RF receiving antenna which is again interfaced to a microcontroller, and from microcontroller I should be writing a set of instructions on the microcontroller to make this car, or the wheels of this car, let me say, rotate left. So if I give an instruction for left, the key pressed is for left rotation, the front wheels should turn left. Maybe if I have to go forward, it should move forward. So I have interfaced different electric motors here, front electric motor, then rear electric motors, then maybe switch on and switch off lights, sirens. So I need speakers, I need LED lights to be interfaced. So all these things are interfaced on the car. So a simple example for what a microcontroller can do, for this is an application specific device. So I have one microcontroller mounted on the remote and another microcontroller on the car, and you can easily control the movement of this car, a simple toy car for example. So this is how a microcontroller is generally useful. So coming to the different types of architectures for microcontroller, what do you mean by architecture? Architecture refers to all the internal hardware organization of a microcontroller. So how we are going to organize the internal hardware, that is architecture. And each hardware architecture will have its own set of software instructions. Normally we call these instructions as assembly language programs, and these assembly language programs will allow us to instruct the microcontroller to do some task. So how do we give a set of instructions? The set of instructions in the microcontroller are given through an assembly language program. Okay, it's called an ALP, assembly language program, and with those instructions the microcontroller will do whatever it is required. Now, what are the different microcontroller families? There are several major families of microcontrollers. What do you mean by a family? A family means a group of products which are put together, which share same internal architectures and who are code compatible. That means I can have 8051, 8052, 8053. So the first version is 8051, then I will make some small changes in the architecture, and so internal architecture will remain the same. There will be some very small changes externally. So, but whatever code you type on 8052 will be compatible, backward compatible with 8050. It should run on 8051 also. That is what I mean by compatibility. So they should be code compatible, they should have the same internal basic architecture. The other things can change, small functionality changes can happen. So manufacturers will usually define variants of the basic architecture. As I told you, 8051 was first, then came 8052 and so on. And hence a family is produced. So code written for one member of the family should be executed on any other member of the family. It should work. That is what we say by compatibility. It should be compatible with all other members of the family. Example families are, so based on the manufacturers, the Zilog manufacturers Z80, it's the oldest 8-bit controller or processor. MC6811 from Motorola, in the 70s it was famous. Today we have the most popular ones as the 8051 belonging to the Atmel 89C51 family, the PIC microcontroller or the peripheral interface controller, the Atmel AVR controller. These are some of the commonly used controllers today. Now coming to the different classification of architectures, we can classify architectures based on different criteria. The first criteria is based on how the memories are used. So based on how memories are used, we are going to classify architectures into two types, the Harvard architecture and the von Neumann architecture. So what is this Harvard architecture? As we are well versed or the well known Harvard School of Education, they came up with this architecture, hence the name. So it's a type of architecture where the instructions or the program code and the data code are stored in two different memory locations. So you have a separate instruction memory, a separate program memory, both are stored differently, and 8051 follows Harvard architecture. Von Neumann architecture is the second type of architecture, and here the instructions or the program memory and the data memory are stored in the same memory area or the memory space. So a common memory space is shared between the program as well as data. A part of it is data, part of it is for the instructions or programs. So all are Intel series of microprocessors, Intel Pentium, AMD, all these follow the von Neumann architecture. So they share a common memory. In Harvard they have different memories. Next, the second type of classification for architectures is based on the instruction set. Based on that, we have complete instruction set and reduced instruction set computing processors. CISC stands for complex or complete instruction set computing. It has a very extensive set of instructions. All regular as well as complex instructions are available to do whatever we want. You can play with the instructions. You have lots of options there. It's a very long instruction set, anything could be done easily. So writing programs or writing the instructions for the processor will become easier. Usually microprocessors will have this CISC architecture, whereas the RISC architecture, as the name indicates, is a reduced instruction set computing, and microcontrollers will normally have this reduced instruction set, mainly because we are trying to minimize the device, we are trying to give specific functionality to the device. So a minimal set of instructions should be incorporated, size and cost would be minimum then. You could reduce the size, you could reduce the cost if you just have a minimum instruction set. That's what is done in RISC architecture. So, but what would be the disadvantage? The complexity level of writing the instructions or program is going to increase. Now, let's see, before talking about the architecture actually, what are the architectural needs for a microcontroller? So, what should be there? What should be present on a microcontroller? Let's see what are the features needed, and based on that we can decide what devices we should put on the microcontroller and its expected applications. If we look at these two things, you can easily decide what are the different things you need to include in a MCU. First thing, sensing the environment, that means an input device or a method to give an input. Say I want to sense the temperature, I want to sense the humidity. So accordingly I should use a temperature sensor or humidity sensor, and I should interface it to my microcontroller. It should be taken as a input, maybe after some processing. Next, once the input is taken, a response should be produced. Say the temperature has gone beyond 40 degrees, I should switch on the AC or switch on the fan. That means a response is needed, and to activate that response an output device will be needed. So the microcontroller will send a signal to the AC or fan asking it to switch on. Because the temperature is sensed and it has gone high, we should need to switch on the AC or fan. And the response sometimes can be delayed. You need not always give the response immediately. So after some time you are monitoring the continuous increase in temperature. Maybe you are monitoring from when it was 35 to when it reaches 40. Only after it reaches 40 you can send the response. So you need to put in delays in the response by using counters or timers. So a counter or timer should be there on a microcontroller, we saw. Next, we need to give prioritized response. Say I am monitoring two things simultaneously. So I am monitoring the temperature and humidity, but I should respond to change in temperature immediately, and humidity change can be monitored or response can be sent a little slowly. So what we need to do? We need to prioritize our response by using interrupts. So which should get first priority, which should get the next priority. Similarly, I am going to write some software or assembly level program to control this microcontroller, and where does that program sit? It should reside in some memory unit. So I have to put some non-volatile memory or ROM. It should not get erased as soon as I change. So surely we need ROM. Then the temporary data can be stored on a random access memory or volatile memory, we call it as RAM. So these are the different things which are needed for a microcontroller to have. So the basic things what are needed, as we saw, an input device, output device or multiple input output devices, timer or counter, interrupts, ROM, RAM are the fundamental needs. And to interconnect all this, you need wires or buses. All these things can be interconnected using wires or buses. So the basic components or the basic architecture of 8051 has, as you can see here, a CPU which is central processing unit. This is where all the arithmetic and logical functions are implemented. A random access memory for data storage temporarily, read-only memory to store the instructions or programs, then the input-output ports where we can give some input and take the output response, timer or delay circuits, counters to have a delayed response or to wait for some time, then serial communication through the COM ports. These are the basic necessities which will be present on one single chip microcontroller like the 8952 one which is shown here in the picture what is shown. So, the 8051 has basically the fundamental things what are present: 4 kilobytes of internal ROM, this one, 128 bytes of RAM, random access memory, 4 8-bit IO ports, port 0 to port 3. So, 4 ports we are going to have, all are 8-bit, 2 16-bit timers or counters and one serial interface along with the CPU. These are the main elements present. Along with that we have many other additional elements present. So, you can see the basic architecture of 8051 will have all these things. As I told you, 2 16-bit timers which will accept counts as input. I can take count 1 and count 2 as input given to both the 16-bit timers. Then we have 128 bytes of internal random access memory to store data temporarily, 4 kilobytes of read-only memory to store the program code, and interrupt control to prioritize our response. Which one should get the first response, which one should get next. We have 5 interrupts together, 3 internal and 2 external interrupts are connected. Then we have the CPU, the main heart of the unit, the central processing unit, which does all arithmetic and logical computations. Then everything needs to be timed to a given clock sequence. So, I need to put a crystal oscillator. You can see here OSC stands for oscillator. A crystal is connected of different frequency to synchronize everything to work at particular times. That is when I can use this oscillator synchronized to timers and everything. When should a read happen, when should a write happen, everything. Then we have bus control. All these interconnections which are shown between them, all these things with arrowheads are called buses. Generally, it is a collection of data lines. What are buses? Buses are collection of data lines and they are used to interconnect the different devices present on the MCU. So, these buses can be controlled. They need to be controlled. When should I send data on the bus? When should I send address on the bus? When should I send some control signal? So, we need so many different types of signals when we need to control the timing of when what should be sent. So, you have a bus control unit. Then, as already mentioned, 4 input output ports, port 0 to port 3, where address and data can be communicated. So, they are input output, that is why it is a double headed arrow. Finally, one serial communication interface with 2 pins, TXD to transmit, RXD to receive. So, this is the basic architecture of 8051. Please remember this architecture. 2 16-bit timers with counts as the input, 128 bytes of internal RAM for data storage temporarily, 4 kilobytes of ROM for program storage, interrupt control unit for 5 interrupts, 3 internal, 2 external, the CPU, the heart of the system, oscillator to have a clock or a crystal connected to monitor all the timing, the bus control unit to monitor how different data flow on different connections or buses, 4 input output ports to take in inputs, data, address, everything, serial communication device, a UART it is called, for transmit and receive serially. The same thing is shown in this diagram also in more detail. Now let's see what are the other features of 8051 which is not implicit in our architecture. It has only one on-chip oscillator or external crystal connected, 6 interrupt sources we say, actually it is 5. To this 5 we are considering the reset signal also as an interrupt signal. So reset, if you press or if you give a high on reset, everything will be beginning starting from 0 or the memory starts from 0. Then we can have 64 kilobytes of external memory for ROM, programmable memory we call it as, program memory or external memory, read only memory 64 kilobytes, and it is controlled using one control signal PSEN. Then we have 64 kilobytes of external data memory. The first 64 kilobytes was external program memory or code memory. This is 64 kilobytes of external data memory. You can read or write from it, but from the code memory you can only read. You can't write into the code memory. It's one time writing. Once you write it for the first time, it is stored permanently. So the control signals here are read-write signals. Then code memory is selectable by another control signal called as external access signal EA. This is the detailed architecture of the 8051 microcontroller. It's almost the extension of the same thing. You have the RAM addressing register here. This is called as the random access memory address register. So it will store addresses of the random access memory. It is connected to random access memory. How it should be addressed? All addresses are stored here. Then this is the B register. Registers are nothing but it's a collection of flip-flops which will help us to store some bits of data. So if I have an 8-bit register, it contains 8 flip-flops to store an 8-bit value. So I can store an 8-bit number at once on an 8-bit register. 8-bit register will have 8 flip-flops connected parallelly. So, or let's say serially, it could be either way. This ACC or accumulator is another 8-bit register. This B is also an 8-bit register. Both A and B together are used to perform basic arithmetic and logical operations. So when an arithmetic operation is performed, they almost always it assumes one of the operands to be there in the accumulator or the A register. The other operand can sometimes be there in the B register. Usually for multiply and divide instruction we need this register, but almost every operation, whether it is add, multiply, and or XOR, whatever, one data or one operand is always there in the A register or the accumulator. Then the output after computing addition or what is passed on to a temporary storage register, TMP2. It's a temporary storage register. So you can fetch data from the RAM, pass it on to the accumulator or the B register, maybe 2 different data to each of them, add them, subtract, do whatever, store the temporary result in this temporary register. So this ALU which is shown here is the arithmetic and logical unit which will perform the actual operation. So the operands are there in accumulator and B register. They are fed through 2 different temporary registers to the ALU which computes or performs the operation, and based on that it will set some flags. So after addition, if there is a carry flag can be made high. If there is an overflow after multiplication, so when I multiply 2 8-bit numbers, the result will be 16-bit. So there will be an overflow from 8 bits. So you have different flag flip-flops, or it's a complete flag register which has multiple flip-flops to store the results of computation. After making some computation, if some flag should be set. It is there in this register called as PSW or program status word. And then we have the interrupt and the serial port and timer blocks here. As I told you, to prioritize the response, you can use the interrupt block, timer to add delays, serial port for serial communication, and you have a stack pointer here. I will tell you what is the use of the stack pointer. Then program address register, this EPROM or ROM stores our program. So the address for where this program is stored is there in this program address register. Then you have a set of buffers, then the program counter and incrementing the program counter, and a data pointer to point to different data locations, timing and control block with multiple control signals connected here, the oscillator to which the crystal is connected. Then I have the 4 IO ports what we mentioned, port 1, port 3, port 0 and port 2. So you can see they are all 8-bit wires connected to all these ports. Port 0 has 8 bits, port 2 here has 8 bits, then port 1 and port 3 again 8 bits. So we have, these are the 4 IO ports. So this is the detailed architecture of 8051. It's just an extension of what we did in the previous blocks, but what we did here, but with more additional details given to this. And coming to the pinout diagram, this is the complete footprint or the pinout diagram. It's a 40 pin IC, the 8051. You can see the compatible families, the other numbers mentioned here. This is called schematic pinout, where port 0, port 1, port 2 and port 3, all the 8-bit are grouped together. So these are the 4 IO ports, the 8-bit IO ports. So already 32 pins are connected here. Then I have these 4 control signals, and then the crystal or the clock is mounted on the remaining 2, that is XTL1 and XTL2. So it is 32 plus 4 36 plus 2 38 and 2 more to give VCC and ground. So totally it is a 40 pin IC. This is called a schematic pinout. Now coming to the detailed description of the architecture which we discussed, we can do it either in the programmer's view. A programmer is a person who writes the code to make the microcontroller work as per his desire. So I want to make the microcontroller as a remote, then I will write the code accordingly. So what am I interested in? The programmer is interested in the memory organization, how the memory is organized, whether data memory and program memory are separate or whether they lie in the same RAM or ROM. The register set, what is the available registers for me to store data temporarily? Registers are used to store temporary data, and it will be used as operands while performing different arithmetic and logical operations. Then the instruction set, how it works, I will be interested. Whereas if I am a hardware designer, my interest points are different. My viewpoint, I need to see what are the different hardware connections. I need to see the footprint or the pinout. I want the timing characteristics. Timing becomes very important. So how efficiently I can make the device work to perform high speed operations. How much time this operation is going to take. How can I reduce the time taken, so on. And the current and voltage or power requirements I am interested in. Can I minimize the power requirement if I do some variation in the hardware? So I am interested in the different hardware connections if I am a hardware designer. So now coming to the details or the specific features of 8051. All the features what we saw in the complete architectural diagram. The detailed architectural diagram, what all features we saw, we are going to analyze now. So what are the different features present in 8051? You should surely remember all these things. It has an 8-bit central processing unit with fundamental registers A and B. A stands for the accumulator, B is another temporary register. Then it has 16-bit program counter, PC stands for program counter, and the data pointer. So, two 16-bit pointers, program counter as well as data pointer. Then it has 8-bit program status word. It's called a flag register. Program status word is nothing but an 8-bit register which stores different flags. Flags are set or reset depending on certain arithmetic or logical operations. So, after addition, if there is a carry, carry flag can be set. If there is an overflow, overflow flag can be set, so on. So, these flags decide the result of certain operations, and it is stored in this PSW or program status word. Then you have a stack pointer. A stack is one specific area in the memory, and you need to have a pointer to point to the different locations in the stack. So, that is an 8-bit stack pointer. As I told you already, 4 kilobytes of internal ROM to store programs, 128 bytes of internal RAM for temporary data storage. This includes 4 register banks, each having 8 registers. So, there are 4 banks together. Every bank has 8 8-bit registers. Then 16 bytes are already there. So, 16 8-bit locations which can be addressed bit by bit. So, if I want to take some data bit by bit and operate on that, I will put it in this area, because all these 16 bytes, every bit of it can be addressed. Every bit, usually we address one byte together. We call one word. One word is 8 bits or 1 byte of data. But if I want every individual bit to be accessed, I should put it in this area of the RAM. Next, we have 80 bytes of general purpose data memory which can be used to store any type of data. So, this is what the 128 bytes internal RAM is made up of. These are the 3 things. Coming to the other specific features, we have 32 I/O pins arranged as 4 8-bit ports, port 0 to port 3. Then 2 16-bit timer or counters, T0 and T1. A full duplex serial data receiver and transmitter. What do you mean by full duplex? Full duplex means data travels in both directions. Data can travel from transmit to receive and from the other side simultaneously. So, when data travels simultaneously, we call it as full duplex communication, both way, two-way transmission. Then we have control registers, also known by the name SFRs, special function registers. So, the other name given to control registers are SFRs or special function registers, and under that we have multiple control registers, timer control, timer mode control, then the serial control, power control, so on. So, we have different types of control registers or special function registers available. Then you have, as I told you, 2 external and 3 internal interrupt sources. If you consider reset, it becomes 6. Then oscillator and clock circuits. So, all this put together gives me the complete architectural features of 8051. Now, let us see what each of them are individually and how it works. So, first let us look into what is an 8-bit CPU along with the registers A and B. So, A and B are CPU associated registers. That means they are the registers which store the basic operands for which the CPU will perform some operation. There are totally 34 general purpose registers on the MCU. Out of these, A and B hold the results of many instructions, especially mathematical and logical operations. I told you, almost always A will contain one mathematical operand surely. The other 32 are divided into 4 register banks, B0 to B3, and each bank will have 8 registers. So there are 4 register banks of 8 registers each. So totally 32 plus 2, 34 registers. Then you have the accumulator. Accumulator is used for addition, subtraction, multiplication, division, bit manipulation. That means in all these operations, accumulator will or should compulsorily have one of the data present or one operand present. The B register is used only in multiply and divide operations. When accumulator is used in multiple operations, B is needed only for these two operations. Next, coming to the 16-bit program counter and the data pointer. What is this program counter? Program counter and data pointers are both 16-bit registers. Each can hold the address of 1 byte of data in memory. So it can be 1 byte of data or 1 byte which contains the program. Program counter will always point to the instructions written in the program. A program is a sequence of instructions. So you will have multiple instructions written one after the other. So a sequence of such instructions is called as a program, and this program needs to be accessed using a pointer. How do I go to where the program is? The program will be stored in some program memory. So I need a pointer which will point to every instruction in the program, bring that instruction and execute it. So the program should be fetched from the excuse me. The program should be fetched from the program memory into the microcontroller, and there it will be executed. We call this as fetch and execute cycle. Next, it contains the address of the next instruction that is to be executed always. Say now currently I am executing the add instruction. So next I should execute what, say I need to perform a jump. So jump on carry. If there is a carry after addition, you should go and do something else. You should jump to another instruction and do that. If there is no carry, then you should do the following instruction. So all this can be obtained if the program counter points always to the next instruction which is written in the program memory. So it will always point to the instructions of the program. Data pointer is made up of two parts, data pointer high and data pointer low. So each one it is going to combine together, it will point to different data locations. That is, it will contain the address of both internal as well as external code and the data which has to be accessed. So DPTR or the data pointer will point to the data and program counter will point to the program. Program is a set of instructions written in the assembly level language. So please remember, you write a set of instructions in assembly level, you store it in the program memory, you use a 16-bit value called as program counter. This program counter will always contain the address of the next instruction that has to be fetched from the program. So the next instruction in the program will be fetched into the main unit, there it will be executed, and later on the result can be stored in the any RAM data memory, and to store that result I will use a data pointer which is also a 16-bit pointer to point to a data memory location to store the result of my computation. Is that clear? So this is how we use the program counter and the data counter. I think we will stop with this today, and we will continue with the remaining parts of the 8051 architectural features in the next class. So until then, you are welcome to come with your doubts and queries. So, thank you.